In uh, everyday life and in science, we always deal with measurements. For example, we talk about the temperature highs and lows for the day. We talk about centimeters of rainfall in a week or in a year, weights, heights, blood pressure readings. We deal with a lot of measurements in everyday life and, of course, in science. Now, when someone says today's high was 73 degrees Fahrenheit, does it mean that it was precisely 73? Could it have been 73.01 or 73.05? Or could it have been 72.99? Measurements can only be made uh, to a certain amount of precision. It's never exact, and that's reality. So, how do we deal with this reality in science and life in general? That's what we're going to see in this section. As we were just discussing, measurements can only be precise to some degree. They're never 100% precise. So, significant digits tell us the number of significant digits indicates the degree of precision of that particular measurement. So let's look at some of the rules that go with significant digits. So let's look at rule number one. Non-zero digits are always significant. So if I say or represent a measurement as 2.35 centimeters, how many significant digits does this measurement have? Every digit here is non-zero. So a non-zero digit is always significant. So suppose I have 3,233 meters height, then every digit here is non-zero, so every digit is significant. Let's look at rule number two. Zeros that follow a non-zero digit and lie to the right of the decimal point are always significant. So suppose, for example, I have 1.2 centimeters. Now, I have another measurement which is 1.20 centimeters. So I'm doing a science experiment and I have these two measurements. What exactly is the difference between these two? They mean the same thing mathematically speaking. They have the same value, but the number of significant digits in the second measurement, which is 1.20, is 3. There is a reason why we have a 0 here. It just tells me that this measurement is precise up to the second decimal place. And even if the value of 1.2 is the same as 1.20, in science, knowing that a measurement is precise up to the second decimal place is very important. So the 0 here is for a reason, and therefore it is significant. Because if they didn't care about that 0, they could have just written the number as 1.2. So this is the reason why if you have a 0 to the right of the decimal point, okay, and this is the non-zero number that the 0 follows, then that's always significant. So 3.00. Let's look at this. There's a decimal point. A 0 after that is there for a reason. A 0 after that is there for a reason. So it would have to be significant. Because if those two were not significant, then your answer would have been just 3 and not 3.00. So how many significant digits does 3.00 have? 3 is non-zero, so it's always significant. And then you have the 0, 0, which are significant. So we have 1, 2, 3 significant digits. Let's look at the next rule. Zeros between non-zero digits or other significant zeros is always significant. So if we have 40003, these are zeros, but obviously they're significant because they are between two non-zero digits that are always significant. What if we have 4000.35? 3 and 5 are significant because they're non-zero. They come after the decimal point, they're still significant. So zeros between two significant digits is always significant. Now, what if you have 400.05? These zeros are significant because the zero here is significant. So this is a significant number, all zeros between two significant numbers is significant. Zeros to the left of the first non-zero digit is never significant. So let's look at an example. Suppose we have 0.0005. This is the first non-zero digit. We have a bunch of zeros before that. All these zeros are not significant. Now, suppose we have the number 0.5000. In this case, by rule 2, these are significant. So I want you to see the difference between rule 2 and rule 4. Now the next one is zeros to the right of the last non-zero digit, but before the decimal point, not significant. So if we have 4000000, so the zeros to the right of this non-zero number is never significant. Suppose we have 210000. All these zeros are not significant. Now, what if I change it and now put a decimal point between the 21 and the bunch of zeros? Now suddenly everything changes, a different rule applies. So therefore, we have all these numbers now significant. That decimal point makes all the difference. If that decimal point is missing, these zeros are insignificant, are not significant, and suddenly if we insert the decimal point there, all these zeros become significant. Now let's look at a few examples. Problem number 1. We have to state the number of significant digits in each measurement and the implied precision. How precise is this measurement is what we have to state. So look at problem A, 90.001. So we have a non-zero digit 9, a non-zero digit 1. So these two have to be significant. Anything in between, if we have zeros in between two significant digits, they are all significant. So how many significant digits do we have? So we start off with the 9. Another one is the 0. Another 0 follows. There's another 0. So there are a total of 5 significant digits. The measurement is precise to the nearest hundredth. So we look at this. So we have tenths, hundredths, thousandths. So it implies a measurement to the nearest thousandth. Look at B, 0.01 centimeter. So we have a non-zero digit, which is 1. So we have 1 as a non-zero digit, and all zeros before the non-zero digit. So if we have only zeros before the non-zero digits, then they are not significant. So we can see 3 digits here, but the first two are not significant. The only significant digit is 1, so the count is 1. So we have just one significant digit. This implies a measurement to the nearest hundredth. So the first digit is tenths, the second digit is hundredths. So we have the next problem. There are only two significant digits because we have 4 and 5, which are non-zero. Everything that follows is 0. So therefore, there are only two significant digits because these zeros are not significant. So now, this year it implies a measurement to the nearest 10,000 years. So that is what it implies. So the 4 zeros at the end indicate that we're counting in 10,000s. So the measurement is, it implies a measurement to the nearest 10,000 years. So problem D, we're given another measurement. This 2 is significant, it's non-zero. The 3 is significant, it's non-zero. Any digit in between two significant digits, even if it's 0, is significant. What about the zeros before 2? Those are not significant. That's by rule number 4. So therefore, let's count. How many significant digits does this number have? It has 1, 2, 3 significant digits. So that's how we get the 3. It implies a measurement to the nearest millionth. So we have, let's do this once again. So that's tenths, hundredths, thousandths, 10,000s, 100,000s, and that is millionths. Since we have 1, 2, 3, 4, 5, 6 decimal places, it is a measurement that is to the nearest millionth.